Hey everybody, this is going to be a dual purpose video. First of all, it's me going to go over the answers, how to get the answers to question 15.58 in Brown-Lemay-Burston, but it's also going to be a video on how to use an ICE chart so that you can either determine the equilibrium constant or you can determine the equilibrium concentrations or the equilibrium conditions. So let's start this. We have a reaction here, and the best thing that we can do when we have a reaction is maybe write the equilibrium constant off to the side. And so keep in mind that this is a heterogeneous equilibrium. So that means that this thing doesn't play a role in the equilibrium. It's not that it's not part of the reaction. Obviously, you need some of that in order for the stoichiometry and the chemistry to happen. But when this reaches equilibrium, the equilibrium isn't going to be dependent on how much calcium chromate is in there. So the equilibrium constant, K, is going to equal the products, Ca2 plus the concentration of the products, over the concentration of the reactants, and in this case, the reactants don't are nothing. So we're going to over 1, right? So this is the K that we're going to be dealing with. So how does an ICE chart work for this? Okay, well, I'm going to write the reaction here. And what's going to happen is I'm going to write an ICE chart. I'm going to make a table, and I'm going to label the top row I, the second row E, and the bottom row E. So this is I, and then I stands for initial. This is how much stuff there is at the beginning. This is C, this is change. That's by how much the stuff that is going to change will change by. And then the last one is E, which sometimes means end, but it actually, I will put it in as equilibrium because we're going to be there. Okay, so we're given the equilibrium constant. Okay, and what we need to do is figure out how much of each of these things at the end there is. How much of this thing and how much of this thing there is at the end. The ICE chart is going to help us get to that point. Okay, so let me get rid of those two things. They look like zeros. Okay, so notice we don't have any information. Okay, this is why you need this video in order to answer this. Okay, you don't have any initial concentrations. The only thing that we have is an equilibrium constant. So we have to make some assumptions. Okay, in order to come up with the equilibrium condition or the equilibrium concentrations, we're not going to need this. This doesn't play a role in the equilibrium, so I'm just going to put an X there. We don't need that value. Okay, and then the other assumption that we're going to make here is that this is going to be 0 and this is going to be 0 to begin with. Initially, how much of each product do we have? Well, we have 0 of one and 0 of the other. If we already had it, there'd be no reason why we were trying to make it. So typically, the initial amounts of each of the products in an ICE chart is 0. Okay, so now what happens when this reacts? Well, when this reacts, some of this stuff will be converted into this stuff. Okay, so that means that these two things are going to gain. This is going to gain some amount. How much is it going to gain? Well, we don't know. We don't know the exact amount, but we know that it's going to gain some amount. Okay, and where is that amount going to come from? It's going to come from here. Okay, so we're going to subtract an amount from this column, and we're going to add an amount in the two products column. Do we know how much? Nope. So it's going to be an X. Okay. How much are we losing? Well, we're losing X. And how do I know that it's just a single X? Well, it's the stoichiometry. The stoichiometry of the reaction says that for every one of these that we lose, we make one of these, and we make one of these. Okay, so the stoichiometry shows us how many x's we gain or lose. If this were 2, the coefficient here would be 2x. Okay, if this were a 4, the coefficient here would be plus 4x. But it's not. It's all 1 to 1 to 1, so that makes it a little more straightforward with the math. Okay, so now how much do we have at equilibrium? Well, since it didn't matter how much of this we had here, and then we're going to subtract the x, it's still not going to matter how much of this we have here, okay, even though we're going to take away some of it. Okay, what matters is that we have 0 plus x equals x, and then 0 plus x equals x. And so how much of this we have at equilibrium is x and x? We don't know. But you know what we do know? We do know that the equilibrium expression, K, is equal to the concentration of calcium times the concentration of chromate. And in the problem, we also have the equilibrium constant given. So this now can be solved just like a algebra problem. We have 7.1 times 10 to the minus 4 equals x, because we have x here, and then this is also x, so x, so that's x times x, so that's equal to x squared, and then we take the square root, of each side. The square root of 7.1 times 10 to the minus 4. Let's see. And you get that x is equal to 0.027. Okay. Keep the same number of sig figs. This has 3 sig figs. This has 3 sig figs. So that is your x. Now you can go back to the ICE chart and figure out, well, the concentration of Ca2+ is equal to the concentration of chromate, because they're both the same, and they both equal x, which is also 0.027 molar. Okay, so that's that's kind of the basics of using an ICE chart for a pretty straightforward problem. Okay, especially with the assumptions. Okay, if you have other questions, feel free to check out more of the answers that I've given you. Have a great day.